the potential of standard hydrogen electrode will be assumed to be 0 at all the temperatures. Concentration of Zn2 plus will be decreasing, the concentration of Cu2 plus will be increasing, the voltage will also keep on increasing. After some time, no changes will be seen regarding to volts. Whenever free energy is greater than 0, rate constant will be lesser than 1 and potential will be greater than 0, it is a non-spontaneous reaction. Hello everyone, this is Harshita Bhavasa from Vidhyaashram PU College, Temple of Excellence. Now, I am going to start session 2 from the chapter Electrochemistry. In the previous session, we have discussed about introduction point for electrochemistry, electrochemical cells and what is electropotential and also about Daniell cell. We have discussed about these concepts and in today's session, we will discuss about measurement of electrode potential, standard hydrogen electrode or normal hydrogen electrode, list of standard electrode potential, importance of standard electrode potential. Measurement of electrode potential. How can we measure the electrode potential? Electrode potential of an electrode can be measured by coupling the given electrode with another electrode known electrode potential, that is reference electrode, and by measuring the EMF of the cell formed. To measure the unknown EMF or unknown electrode potential, first you have to have a reference electrode with known electrode potential. After that coupling, a cell will be formed. By that, measurement of electrode potential can be done. Also, electrode potential of the given electrode could have been measured if the reference electrode has potential. Since no reference electrode can be set with its potential equal to 0, the absolute electrode potential cannot be determined. Here, electrode potential of the given electrode could have been measured if the reference electrode has potential, but no reference electrode will be equivalent to 0, so the absolute electrode potential cannot be determined. It will be related to electrode potential, not absolute potential. Therefore, potential of an electrode is measured relative to standard hydrogen electrode whose potential is assumed to be 0 at all temperature. Since we cannot set with the potential equal to 0, we will measure with relative to the standard hydrogen electrode which is assumed to be 0 in that electrode at all the temperatures. So, we will take the reference for standard hydrogen electrode which its potential will be assumed to be 0 at all temperatures. Next, standard hydrogen electrode or normal hydrogen electrode. First, we will see the construction. Hydrogen electrode is the primary standard reference electrode. The platinum foil is coated with platinum black to increase the absorption of hydrogen gas on its surface. Hydrogen electrode will considered as primary reference electrode. The platinum foil is coated with black. Here, the platinum coil is coated with black to increase the absorption of hydrogen gas on its surface. Adsorption means any of the substance will get absorbed, will get fixed on the surface, will not penetrate into the any of the material. That process will call it as adsorption. There is a little bit difference of between adsorption and absorption. Adsorption means only will be adsorbed on the, only will settled on the surface of the material. Mercury is used to make or break the contact of standard hydrogen electrode with another electrode easily. Here mercury is present. Why mercury is present means to make or break the contact with another electrode which the electrode potential has to be measured. The platinum foil is partially immersed in 1 molar hydrochloric acid and hydrogen gas is bubbled just below the surface of hydrochloric acid to maintain the partial pressure of hydrogen at 1 bar. That overall platinum coil which is coated with black will be immersed, partially immersed in 1 molar hydrochloric acid which is a HCl and hydrogen gas is bubbled. Here hydrogen gas is bubbled just below the surface of hydrochloric acid. Why it will be bubbled there? To maintain the partial pressure of hydrogen at 1 bar. This is the standard hydrogen electrode. Here hydrogen gas is bubbled, here mercury is present, and here over platinum coil is coated with black. Next, working. Hydrogen gas bubbled is adsorbed on the platinum surface. Hydrogen ions of HCl solution will be equilibrium with the hydrogen gas as given below. We know that hydrogen gas will be bubbled, is adsorbed on the platinum foil, and later hydrogen ions of hydrochloric solution will be in equilibrium with the hydrogen gas as given below. See here hydrogen with electrons, and here half of the hydrogen will be in equilibrium. The potential of standard hydrogen electrode is arbitrarily assigned to be 0 at all the temperatures. The potential of standard hydrogen electrode will be assumed to be 0 at all the temperatures. Electrode potential of given electrode is measured by coupling it with standard hydrogen electrode and measuring the EMF of the cell formed. Now, standard hydrogen electrode has been set for 0 at all the temperatures, and the unknown electrode potential has to be measured, and that should be coupled with this SHE, and their EMF will be formed between the cell formed, and later it will be measured. The potential of the given electrode is equal to plus EMF if she is anode and minus EMF if she is cathode. Here positive EMF will be in anode and negative EMF will be cathode. According to convention, symbolic notation of standard hydrogen electrode is here platinum with hydrogen gas and hydrogen gas of HCl with 1 molar solution. Next, determination of electrode potential of zinc by using standard hydrogen electrode. How to find out the standard electrode potential of zinc by using She? The standard hydrogen electrode is the reference electrode. We know that it is a reference electrode. The given zinc electrode is coupled with She. The given zinc electrode will be coupled with She. The EMF of the cell is measured using a potentiometer, and it is found to be 0.78 volt. Here the EMF of the cell will be measured by potentiometer, and its volt should be 0.78, which will be found in that. In this cell, zinc electrode is negative relative to the hydrogen electrode. Electrode is calculated as below. Here zinc electrode is negative. E naught cell equal to E naught cathode minus anode, that is reduction minus oxidation. Cathode is in reference, so reference minus the unknown electrode potential. Next, that is She electrode and cell which is formed. It will be at arbitrarily equal to 0, and this is 0.76 volt. So minus 0.76 volts will be present. Anode half of the reaction zinc, and it will be given out electrons, zinc 2 plus 2 electrons. Cathode half cell reaction, here hydrogen plus 2 electrons will be added, H2. Overall cell reaction H plus Zn, that is zinc, gives rise to hydrogen plus Zn 2 plus. Cell notation Zn in Zn 2 plus and hydrogen in hydrogen gas with platinum foil. List of electrode potential. If you see the textbook, you have the overall list of electrode potential. Here I have not given the overall list of electrode potential, just I have given with the negative sign, with 0, with positive sign. Okay, what are the terms and why it will be 0? If it is 0, what is its significance? If it is minus with the negative sign, what is its significance? If it is with positive sign, what is its importance? We'll know here by seeing some of the examples. Overall list will be given in your textbook. List of standard electrode potential. Standard reduction potential of half cell, which is the ionic concentration, are at 1 molar in water at 25 degree Celsius. This is overall oxidizing agents, and here reducing agents, and this is volts. Here, which is having a negative sign will be the strong reducing agent, and which is having a positive sign will be the strong oxidizing agent. This is the major significance of negative and positive sign. Once again, which the value with positive sign is a strong oxidizing agent, with negative sign it is a strong reducing agent after the coupling with hydrogen gas. Next, importance of standard electrode potential. We have seen some of the significance of electrode potential and what are the major importance. The values of standard electrode potentials E0 can be used to predict the ability of the species as an oxidizing agent or reducing agent. By seeing the values of electrode potential in the list, you can able to identify which is the strong oxidizing agent, which is the strong reducing agent. Higher the standard electrode potential, greater is the oxidizing agent. Okay, when the standard electrode potential is in higher value, it will be having greater oxidizing ability and lesser is the reducing ability. The table, the electrode potentials of species decreases from top to bottom and therefore the oxidizing power of the species decreases. If you see the table, top to bottom, the values will be decreasing, so the oxidizing power will also decreases. On the other hand, reducing power of the species will keep on increasing. Down the side, negative values are there, so the values will be decreasing, reducing power will be increasing, but oxidizing power will be decreased. For example, the standard electrode potential for fluorine has the highest value, indicating the fluorine gas has the maximum tendency to reduce to fluoride ion, which is having, the fluorine is having highest value, so it is having the maximum tendency to get reduced to fluoride ion. And therefore, fluorine gas is the strongest oxidizing agent and fluoride ion is the weakest reducing agent. Lithium has the lowest electrode potential, indicating that lithium ion is the weakest oxidizing agent. One is fluorine, highest value, so it will get reduced very easily, and here lithium with lowest electrode potential, indicating lithium is the weakest oxidizing agent. If the electrode potential of an element is greater than 0, then its ion is reduced by hydrogen. If the standard electrode potential is greater than 0, that ion will get reduced by hydrogen. If the standard electrode potential of an element is negative, then hydrogen ion is reduced by the metal to hydrogen gas. If it is less, it will reduce to hydrogen gas. If it is more, reduced by hydrogen gas. This is the importance of standard electrode potential. Next, NERNST equation. For electrode reaction, Mn plus in the aqueous region and number of electrons gives rise to metal solid. The electrode potential at any given concentration can be calculated using NERNST equation, is given by E equal to standard electrode potential minus RT by NF ln concentration of product divided by concentration of reactant, but concentration of solid metal M is taken as unity and we have here this one will taken as unity and we have written the same equation whatever we have written here, but what are the terms and what does it refers to? E0 Mn plus Rm is given standard potential of electrode, R molar gas constant which is having the value 8.314 joules per kilo per mole, T temperature in Kelvin, F Faraday constant, N number of electrons involved in electrode reaction, Mn plus concentration of metal ion, capital M concentration of pure solid metal taken as unity. This is very important equation and you have to know the terms which are involved in this equation. Next, relationship between the equilibrium constant and E0 cell. In galvanic cell involving the net cell reaction of the type A plus B gives rise to C plus D. NERNST equation can be written as E equal to standard electrode of the cell minus RT by NF ln concentration of product by concentration of reactant. So, you have to analyze E0 cell, that is standard electrode potential. So, we are taking to left hand side RT by NF ln Kc or E cell equal to E0 cell minus RT NF ln Q. Then what is the Q? Q is the coefficient reaction quotient. So, concentration of product by concentration of reactant. So, Q is reaction quotient. At equilibrium, E cell will be equal to 0, the reaction quotient Q equal to Kc, where K is the equilibrium constant. So E naught cell will be equivalent to RT by NF ln Kc, or E naught cell equivalent to plus 2.303 RT by NF log Kc. That ln will be converted into log. From the ln to log conversion, 2.303 value is required. This equation gives a relationship between equilibrium constant of the reaction and standard cell potential of the cell. At temperature T equal to 298 Kelvin, F equal to 96,500 coulombs and R equal to 8.314 joules per kilo per mole, the above equation can be written as E naught cell equal to 0.0591 divided by NF into log Kc. If you put these standards in this equation, overall this equation will be given out. These are both important equations, and from this you may expect the numericals also. In Daniell cell, at any given concentration of Cu2 plus and Zn2 plus ions at 298 Kelvin for the net cell reaction, Zn plus Cu2 plus gives Zn2 plus Cu. NERNST equation is given by E cell equal to E naught cell minus 2.303 RT by 2F log into concentration of product by concentration of reactant. Here in the Daniell cell, zinc and copper will be taken in the electrodes. So for that we are applying the NERNST equation. Here 2 electrons will be involved. So N equal to 2. We are applying those reaction in the NERNST equation. So E cell equal to E naught cell minus 2.303 into 8.314 into 298 Kelvin divided by 2 into the standard Faraday 96,500 into log concentration of metal in the product side by reactant side. So overall what will happen? E cell equal to E naught cell minus 0.0591 divided by 2 into log, that is concentration of product by concentration of reactant. If you multiply this much of values with the standard, these are the all standard values. If you multiply this one, you will get this value. In Daniell cell, when the circuit is closed, the concentration of Zn2 plus keeps on increasing while the concentration of Cu2 plus keeps on decreasing. In the Daniell cell, the concentration of Zn will be keep on increasing, the concentration of Cu will be keeps on decreasing when the circuit is closed. At the same time, voltage of the cell as read on the voltmeter keeps on decreasing. Here in the voltage also keeps on decreasing. It will be shown in voltmeter. After some time, we shall note that there is no change in the concentration of Cu2 plus. Concentration of Zn2 plus will be decreasing. The concentration of Cu2 plus will be increasing. The voltage will also keep on increasing. After some time, no changes will be seen regarding to volts or concentration. Cu2 plus and Zn. Voltmeter also gives 0 reading. This indicates that equilibrium has been attained at which E cell will be equal to 0. If voltmeter is showing 0, the concentration, if it is not at all changing in reactant or product side, then the reaction has been reached to equilibrium. E cell will be 0, so it will be K into E. E cell equal to 0.0591 divided by 2 log into Ke. Means it has been reached to equilibrium. Next, relationship between standard free energy change and standard electrode potential, E naught cell. The electrical work done, W in joules, is the product of the potential difference, E cell in volts, and the charge cell that flows in coulombs. W max, that is maximum work done, equal to potential in volts into charge. The maximum work done on the surroundings is equal to the decrease in free energy. Whatever the maximum work done is on the surroundings will be equal to decrease in free energy. So it will be designated by negative sign. W, that is work, maximum work will be equal to minus into free energy. So we have, if you want to find out free energy, E cell will be here, free energy will be equivalent to E cell into charge, but charge will be equivalent to NF. So free energy change in free energy will be equivalent to minus NFE, not of the cell. Okay, this is about free energy and electrode potential difference. And here free energy and equilibrium constant relationship we can find out. We know that E naught cell equivalent to 2.303 RT by NF into log Kc. E naught cell equivalent to minus delta G naught by NF. So minus delta G naught, that is free energy, by N into F equal to 2.303 RT by NF log Kc. So NF cancel out each other. So delta G naught equal to minus 2.303 RT log into Kc. See here, reaction parameters at the standard state. Whenever free energy is lesser than 0, rate constant will be greater than 1 and standard potential will be greater than 0, that reaction will be spontaneous. When free energy will be equal to 0, rate constant will be 1 and electrode potential will be 0, it will be at equilibrium. Whenever free energy is greater than 0, rate constant will be lesser than 1 and potential will be greater than 0, it is a non-spontaneous reaction. You know what is spontaneous reaction, non-spontaneous reaction, as well as at equilibrium. So you have to relate this reaction with these reaction parameters. Next difference between EMF and potential difference, that is voltage. EMF is the potential difference between two electrons when no current is flowing in the circuit. Whenever no current is flowing in the circuit, that potential difference will be considered as EMF. It is the difference of the electrode potential of the two electrodes when the circuit is under operation. Voltage is when circuit is under operation, we will consider as voltage. Whenever it is not under operation, that will be considered as EMF, electromotive force. It is the maximum voltage that cell can deliver. It is always less than the maximum value of voltage which the cell can deliver. It is responsible for the steady flow of current in the cell and it is not responsible for the steady flow of current in the cell. It is measured using potentiometer, it is measured using voltmeter. These are the major difference between EMF and voltage. Next, uses of electrochemical cells for the determination of pH of the solution. To identify the strength or to identify the acidity or basicity of the solution, we use electrochemical cells. To determine the solubility product, to determine equilibrium constant, for potentiometric titrations and other thermodynamic properties. So, electrochemical cells will be used for to identify pH of the cell, solubility product, as well as equilibrium constant and potentiometric titrations and other thermodynamic properties. Now, we will see the numericals. A zinc rod is dipped in 0.095 molar solution of zinc sulfate at 298 Kelvin. Calculate the electrode potential of zinc electrode which is having the potential of minus 0.76 volts. We have to analyze through NERNST equation. So, potential of cell will be equivalent to electrode potential minus 0.0591 divided by 2 into log of 1 by concentration of reactant. So, here potential of cell will be equivalent to minus 0.76 because electrode potential they have given already minus 0.76 volts, minus 0.591, it is constant taken from equation, divided by 2 because 2 electrons will be involved in the reaction, into log of 1 by 0.095. Here zinc concentration they have given, so we have written here 0.095 concentration. Here minus 0.76 minus, after calculating 0.0591 divided by 2, this much, into log of 1 by 0.095, here 1 by this much 10.526, and after calculating here log 10 will be present, so log 10 1.0224, here you have to do multiplication and later minus 0.76 minus 0.03021. So, overall will be potential of that cell will be equivalent to minus 0.79021 volts. So, in the next session we will discuss about conductors, types of electrolytes, conductance of electrolytic solutions, and measurement of the conductivity of ionic solutions. I hope you have understood completely whatever I have taught in this session. We'll meet in the coming session. Thank you.